Let's look at the function f of x equals x squared plus 2. So that's a parabola that's been shifted up 2 units, and the graph looks something like this. And look at this shaded area right here. Well, the goal is to calculate the area of the shaded region. And we had been approximating the area by looking at a bunch of rectangles. And remember that more rectangles was a better approximation of the area. Well, what if we had infinite rectangles? That should give us the exact area. So here's the function, and here's the graph again. And we're going to look at right endpoints, and we're going to look at using an infinite number of rectangles. Now, how are we going to do that? Well, if we use the letter n to denote the number of rectangles, and we let n go to infinity, that would be a way of giving us an infinite number of rectangles. And so you can imagine that there's probably going to be some kind of a limit going on here, a limit as n goes to infinity. So here is a rectangle, and we can say that's rectangle number 1, and then we have another one that's rectangle number 2, and notice we're using right endpoints. Here's rectangle number 3, rectangle number 4, and I'm not going to draw in anymore because remember I want to have n of them, so I don't want to have a specific number. I'm just going to let it be some generic number n. But eventually, if we had n rectangles, we would eventually get to rectangle number n. That would be the last one there. And so what's the width of each of these rectangles? Well, we know that delta x represents the width of a rectangle, and we could say that's b minus a over n. So what are b and a? Well, if I let the endpoints of the interval that I'm looking at, so in this case 1 to 3, and I let 1 be a, so this is the same thing as a, and if I let 3 be b, so these are the endpoints of the interval where I'm trying to find the area here, then b minus a over n should give the width of each rectangle. Remember, we have n rectangles, so if I divide up this length right here into n different little slots here, then that would be 3 minus 1 over n, or 2 over n. That's the width of each rectangle when I have n rectangles. Now what about the height of each rectangle? Well, imagine I look at this x-axis from 1 up to 3. So if I call this 1 right here and I call this 3 up here. So I'm looking at this portion of the x-axis right here. And when I do that, remember that I have an n rectangles. And so if I start over here, the first rectangle maybe would be right here, and then the second one would be right here, and then the end of the third one would be right here. And remember, I'm using right endpoints, so it's these locations that determine the height. So this rectangle that's right here, this one that would extend up here, this is the part that determines the height, the right end of the rectangle. And we probably should have some notation if we're going to try and figure this out. We need to say something about it, otherwise it's going to be hard to write an expression for it. So let's say that this is x sub 1 for the first rectangle. And then this one would be the location of x sub 2. And this one could be x sub 3. And so on until we get to some generic one in the middle here. I can just call it x sub I. How about that? Just for the ith rectangle. So this is just some place in the middle here. Because remember, I have n of them. So we need some generic labeling here for rectangle number I. And then to get the height, you put in the value of the function at that position. So we could say the height of each rectangle is f of x sub I, where I goes from 1 up to n. Okay, so we have the area of a rectangle as being the height times the width, and we just saw that the height can be represented as f of x sub I, and the width is delta x. And we know that that width, delta x, is really 2 over n. And that f of x sub I, well, I know that the function itself is x squared plus 2. So you can see that up here, x squared plus 2. So f of x sub I would be x sub I squared plus 2. So something like that. Okay, so we're going to make a little chart here of I and x sub I and see if we can actually write out x sub I in a way that's going to be a little more illuminating here, some way we can use it for a calculation. So bear with me here. This is going to seem a little bit abstract. It might seem a little difficult at first. You might have to go through this a few times to actually understand what's going on. But see if you can get it. So, okay, we have rectangle number 1. So let's look at that x-axis again from 1 up to 3. So remember, this is 1 right here, and this is 3. And the width of each rectangle is 2 over n. Well, that means that the first rectangle, which is right here, remember we're looking at right endpoints. This is the right end of that first rectangle. That would be this. If I were to kind of draw in a rectangle here, maybe something that looks like this, and this right here is where I'm looking at right here. Well, that would be 1 plus the width of a rectangle, which is 2 over n. Right? The width is 2 over n, this is 1, so if I go over a distance 2 over n, I have 1 plus 2 over n. That's the value of that coordinate right there. So I can put that in my chart here. Rectangle number 2. So this is when I equals 2. So now I go over another 2 over n. So now I'm looking at this right here. That would be for rectangle number 2, and I have to add another 2 over n when I go over that distance. So I get 1 plus 2 over n plus 2 over n, or I can rewrite that as 1 plus 2 times 2 over n. And for rectangle number 3, that would be maybe right here. And so now I'm looking at this coordinate here. And again, I have to go over a distance of 2 over n. Each of these distances here is 2 over n. So I have to add another 2 over n, so I get 1 plus 2 over n plus 2 over n plus 2 over n, or 1 plus 3 times 2 over n. Well, now I keep going here, and eventually I get to rectangle number I. So that's somewhere in the middle here. Remember, I have n of these total. So this is somewhere in the middle. Rectangle number I is positioned right here, the right endpoint. And so you can see the pattern here if you look at this, if you look at the chart. So we have 1 plus 2 over n, 1 plus 2 times 2 over n, 1 plus 3 times 2 over n. Notice the 3 here, and the 3 here, the 2 here, and the 2 here. So if I have an I here, I'm going to have an I right here. So this is 1 plus I times 2 over n. And I can rewrite that as 1 plus 2i over n. Okay, so now I can say that the area of a rectangle, which was x sub I squared plus 2 times 2 over n, is actually 1 plus 2i over n quantity squared plus 2 times 2 over n. So I just figured out what that x sub I was. Well, that's the area of a single rectangle, but I have n rectangles. Well, it's pretty easy. I can just sum all of them up. So I go from I equals 1 up to n, and that will be adding up the area of each of the n rectangles. But I wanted an infinite number of rectangles. And remember, we were going to have this value n that was going to represent the number of rectangles, and now I'm going to let n go to infinity. So the exact area should be this intimidating looking expression here. We have a limit as n goes to infinity of the sum from I equals 1 to n and then we have something that represents the height times something that represents the width. So remember, this part right here is the height, and this 2 over n, that's the width. So this looks a little scary, but it's totally doable, and we're going to try and calculate this right now. So here we go. So we have the formula for the exact area. And remember, we're using right endpoints here. And we're going to use these special sums. Now I have the special sums written in terms of k equals 1 to n, and you'll see k's in here. But remember, this is a dummy variable. I have an I here, so just replace the k with an I everywhere, and the same formulas hold. So the area, I'll call that A, is going to be equal to this thing right here. And the limit, remember, I'm not going to do anything with that until the very end of the problem, because that'll be the last thing I work on. And now I have the sum from I equals 1 up to n. That's the adding up the n rectangles of. Now I have this thing squared. Let's square that out. So I have a 1, and then I'm going to have 2i over n times 2i over n, or plus 2i over n, sorry, for the cross terms. So here, I'll write this out up here so this doesn't get too confusing. I'm doing 1 plus 2i over n times 1 plus 2i over n. Okay, so I just did 1 times 1, that gave me 1. Now I have 1 times 2i over n plus 1 times 2i over n. That's going to be 2i over n plus 2i over n, or 4i over n. So that'll be my next term, 4i over n. Okay. And then lastly, I have 2i over n times 2i over n. That's 4i squared over n squared. Okay, that was plus 2, and then all of that was times 2 over n. Okay, so next line down, let's try and simplify this a little bit more. Remember, I'm just going to keep writing the limit here until the very end. You can just kind of ignore it. Times the sum from I equals 1 up to n of. Okay, so I have a 2 and a 1 here. That can become a 3. And then I want to distribute this 2 over n. So if I have a 3 here, and I multiply that by 2 over n, that's going to be 6 over n. So that'll become a 6 over n plus, and then this will be 8i over n squared when I distribute. Okay, and then this one right here, that's going to be 8i squared over n cubed. Okay, now at this point, this sum only cares about I. I is sort of the variable that is representing the sum here. The n is a constant in a sense. It's just the number of rectangles that we have. So the sum really only cares about I. Everything else we can pull outside of the sum. So if I want to, I can rewrite this as the limit. Remember, that limit just keeps hanging out until the end. You can kind of ignore it. Keep writing it, but more or less ignore it. Now I have the sum of 6 over n. So if I want to, I can pull out the 6 over n. That's all constant. And then I just have the sum. And it's from I equals 1 up to n. And then I would just have a 1 there if I pulled out the 6 over n. Breaking up the sum here. I'm doing the sum of each of these 3 terms individually, and I'm factoring out the 6 over n. The next one I have 8i over n squared. Well, that I has to stay, but the 8 over n squared, that can come outside. The sum doesn't care about the 8 or the n squared. So I equals 1 up to n of plain old I. And then the last term, I have an 8 and an n cubed that can come outside. So I can put an 8 here and an n cubed here. And then I have the sum from I equals 1 up to n of I squared. All right. Next line down. Keep writing the limit. So we're not doing anything with that limit until the very end. Now I have to evaluate each of these sums, and that's where I'm going to use these formulas right here. Remember that in place of the k, you can put the I if you want. So I have the sum of a constant, so I'm going to use this formula. I have the sum of just plain old I, or plain old k, and I have the sum of I squared, or k squared. So I'm going to use those 3 formulas. So I'm going to have the limit of 6 over n times, and the sum of a constant is just the constant times n. The constant in this case is 1. That's going to just be plain old n. Next I have 8 over n squared times, and now I have the sum of I. Well, that's going to be this. Remember, think of this as an I, so it's n times n plus 1 over 2. Okay, so that goes in here, n times n plus 1 all over 2. And then the last term, I have my 8 over n cubed. And now I have the sum of I squared. That's this formula right here, so it's going to be n times n plus 1 times 2n plus 1 all over 6. And then I'm going to take the limit of that whole thing. Well, now this is just a limit with something in terms of n. I mean, it's a little messy. You're going to take some algebra here, but it's something you totally know how to do. So let's try and simplify it a little bit, and then we'll take the limit of the whole thing. So again, I'm going to rewrite the limit out front until I'm ready to actually do the limit. So the limit as n goes to infinity of, and I have 6 over n times n, that's plain old 6. And then I have an n squared and an n, one of those will cancel, so I'll still have an n down here. So I'm going to have, and the 8 and the 2 also can cancel, so that'll make a 4. So I'm going to have 4 times n plus 1, and then on the bottom it's just going to be plain old n, because I canceled out one of those n's right there. And then over here, plus I have an 8 and a 6. That can become a 4 and a 3. So it'll be 4 up top, and then it'll eventually be a 3 on the bottom. But let me write the top first. One of these n's is going to cancel. So I'm going to have 4 times n plus 1 times 2n plus 1. And then the bottom, that's going to become a 3, and that's going to become an n squared. All right. Almost done here. So now I have the limit as n goes to infinity of this whole thing. So let's try and simplify this a little bit further. Maybe give everything a common denominator. That might be good. So I want an n squared here at least for my common denominator, maybe even a 3. So if I want a 3n squared, this is going to become 18n squared. 6 times 3 is 18 over 3n squared plus. And then here I'm going to have, let's see, I have a 3 and an n I'm going to need. So that's going to be 12n over n plus 1 over 3n squared. So this might not be the easiest way to do things, but at least it's clear, makes sense. And this I don't need to do anything with. I already have the 3n squared, although I could multiply this out. That might be nice. So let's do that. I would get 2n squared, and I would get cross terms of n and 2n. That would be 3n when I add them together, plus 1, all over 3n squared. Okay, so now I have the limit as n approaches infinity of, all of this is over 3n squared. So I'm going to get 18n squared plus, and I'll multiply this out, this will be 12n squared plus 12n plus 8n squared plus 12n plus 4 all over 3n squared. And now, if you look at this, remember we're doing an infinite limit, so it's really the highest powers of n that are going to matter here. And as n goes to infinity, I see the highest powers in the numerator and denominator are both n squared. So it's actually just the n squared terms that are going to survive when I do this limit. And on the top, I have 18n squared, that's the first term here, plus 12n squared plus 8n squared. And if you add all of this together, 12 plus 8 is 20 plus another 18, that's going to be 38. And then I'm going to have a 3 on the bottom. And so when you do this limit, you're going to get 38 thirds. And that seems like a lot of work to just get this nice simple answer here, but that does represent the actual area under that curve from x equals 1 to x equals 3. Okay, so here's the function again, and here's the area we just found, and we saw that the exact area was 38 thirds. So a couple questions you might have here. What if we used left endpoints instead of right endpoints? Well, it turns out that you get the exact same answer. In fact, you could even use midpoints, or you could even use just some random point to determine the height inside each width of each rectangle. And this seems like a lot of work. Is there an easier way? And in fact, there is a shortcut, but it's not as illuminating as this way is. This actually shows you where that area comes from. So for now, this is the general formula to find the area under a curve. You take the limit as n goes to infinity of the sum from I equals 1 up to n of f of x sub I, that represents the height, times delta x, that represents the width.